Hi guys, in this video we are going to start on the organic chemistry, but this time it is part 2. So in our previous videos we have talked about isomerism and the functional group chemistry. So basically you have learned all the chemical reactions in organic chemistry. So starting from part 2 here, we will start from the organic synthesis. So this topic, the first part here, we try to talk about interconversions. Now, interconversions basically is an application of all the reactions that you have learned, and we try to improvise, we try to think, how can we convert organic compound A into organic compound B, all right? It could take only one step, but it could also take 2 or even 3 steps, okay? So basically it is an application of all the reactions that we have learned, okay? So you can take this one as a revision or consolidation of all the reactions that you have learned, okay? So let's get started, okay? Now, first of all, we say that organic synthesis, now synthesis basically means production, okay? So organic synthesis is the conversion of a starting carbon compound into a target carbon compound. So like I said, A to B, right? Now, we say that some reaction, okay? For example, if I want to have like A becoming B, all right? So it could be a one-step reaction, just A becomes B, just one step, and it's done, all right? But sometimes A may require to first convert it into X, and then perhaps X converted into Y, and then at last Y converted to B, all right? So it takes several steps. It takes several reactions to actually change from A to B, all right? So in this part here, in organic synthesis, we are trying to improvise the reaction pathway or reaction route as to how to convert A into B, okay? 1 step, 2 step, or maybe 3 steps, okay? Now in DSC syllabus, we are expected to have at most 3 steps, okay? So that's why you need to know the chemical reaction very well. Otherwise, you cannot think about the synthetic route, okay? Now, so here, similar idea. Some syntheses, okay, this is the plural, syntheses, only take 1 step, but many syntheses require several steps, okay? So we try to draft or design a synthetic route in order to show all the necessary steps, necessary reaction, okay, in order to accomplish such a conversion, okay? Now, when we are trying to describe the synthetic route, we must show very clearly these 4 items if they are available. Now, of course, the first one, the major organic compounds, this is necessary. Like I said, you try to change A into B, right? So you must show to people the structure of the starting compound and also the structure of the target compound. So it's A and B, okay? Now, intermediate here, it is basically the organic compound that is formed during the synthesis, during the reaction pathway. For example, if you go back to here, now we say that, oh, if you want to change A to B, probably you need to first change it into X, and then you change X into Y, and then Y at the end, change it into B. Okay, so we say that X and Y, these 2 are the carbon compound during the synthesis. So these 2, they are not the starting compound, they are not the final compound, and these 2 are what we call intermediate, okay, something in between, intermediate. So we're talking about X, Y, okay, if you try to follow this representation, okay? So in our synthesis, in our synthetic route, we must show very clearly the structure of all these carbon compounds, okay? Now, The next one is, of course, the reagents. Most of the conversion requires a reagent. So you need to specify, you need to show it. Catalyst, some reaction requires a catalyst, you also need to show it. And lastly, the condition. Sometimes the condition may require a specific solvent. For example, if you remember, for the reduction of aldehyde or the reduction of carboxylic acid, we use lithium aluminum hydride, LiAlH4, right? Now, if you remember, this particular reagent is highly sensitive to water. So when we are using this lithium aluminum hydride, we must first dissolve it in dry ether. And this dry ether is the necessary solvent for performing the reduction reaction, okay? So you need to specify. Acetic alkaline medium, the very common one is the potassium dichromate and the potassium permanganate. Very often, we will use acidified potassium dichromate, acidified potassium permanganate. So this is what we call the acidic and alkaline medium. Some reactions require heating. For example, dehydration. Dehydration, we must heat it. Or oxidation, something like that. Later on, I will tell you what type of reaction must require heating in DSE. Okay? UV light, if you remember, for alkane, the free radical substitution reaction requires UV light to kick off the first step, the initiation step. Okay, so UV light is the necessary condition for free radical substitution reaction. Okay, now let's have a look at a synthetic route. Look at this synthetic route. Now, first of all, what we are trying to do is to change propan 1 node to propane. Okay, propan 1 node to propane. So this is the starting compound, propan 1 node, will show the structure, and the target compound would be propane. Okay. Now, so we cannot do this in one step. We need to have at least 2 steps. So the first step is we try to change it into propene by performing a dehydration reaction. So here, the aluminum oxide here, you see I use green color. I try to match the color with a type of information that we need to include. So here, aluminum oxide is a catalyst because if you remember, for dehydration we have dehydration and we also have catalytic dehydration. One, we use a dehydrating agent such as corn sulfuric acid. Another one, we use a solid, which is either aluminum oxide or we can use pumice stone, right? So this is considered as a catalyst. And for dehydration, we require heating. So heating is the condition, right? So we will show the catalyst and the condition on the arrow. So you either put it on the top or at the bottom. Usually you put one each, okay, top, bottom, okay? So then it will be converted into the propene intermediate, okay? Then what we're gonna do with the propene is that we use hydrogen to perform the hydrogenation, which is a type of addition reaction. So hydrogen is the reagent because the hydrogen actually reacts with the propene to form the propane. As a matter of fact, the hydrogen will be added into the carbon, okay? And platinum here, again, is the catalyst. Okay? If you use platinum, you don't need to heat it. If you use nickel, you have to heat it to 150 degrees Celsius, okay? So that's why we need to also include the platinum. You can put it here, you can also put it at the bottom, okay? So this is how a synthetic group looks like, okay? Now, a couple of remarks. First of all, you see, are these chemical equations? Of course not, because obviously they are not balanced. But it is perfectly fine. For synthetic routes, we are not writing chemical equations. So it is perfectly fine to have it unbalanced. As a matter of fact, you only have to show the major organic product. So even though you may have some side product, for example, this reaction, actually you also produce a molecule of water, okay? But you don't have to show that water okay, in the synthetic routes. We only focus on the organic compounds, okay? And you also notice we don't have to consider the stoichiometry, right? 1 mole, 2 mole is not necessary. And actually there is one more thing. We don't need to pretty much consider the yield, okay? We don't really pretty much consider the yield. But this one, I will talk about it later if we come across a question like that. Because some reaction could produce side products. But for synthetic routes, of course, we will try to perform the reaction with the highest yield, but it is not 100% necessary. Okay, we will talk about that later. Okay, so yeah, so let's have a look at down here, these 2 pages. Now you see a huge table. They are actually coming from this one, actually with the CAC guide. Okay, this one is for teacher, basically telling us that what kind of reaction do the HKEAA expect us to teach. In other words, what kind of reaction will be examined in the DSE exam, and also what are the expected way of answering these questions. So, you know, I understand perhaps some of you may have tutorial classes outside. They probably have different version, different way of saying. For me, I will always stick with the official guidelines to the teachers. And I would always teach based on this official document. So if you ask me, oh, is it okay to do it this way? Is it okay to do it that way? Of course, if it doesn't work, I will let you know. But if it works, but it's not the same as the guide, I will always say that, okay, I will always follow the guide. So for that one, I do not recommend you to put it. But if it really works, I will still mark it as correct. But again, strongly recommend you to follow this guide, okay? All right, so have a quick look and also take it as a revision because that kind of summarizes all the reactions, conditions, catalysts, and also the conditions, of course. Now the first one, alkane. Now you see alkane can be converted into haloalkane by reacting with a halogen in the exposure of UV light or heat, okay? UV light or heat. And here the halogen, you see, this is the remarks for us teacher. We are talking about bromine and chlorine, Iodine, the syllabus doesn't need you to recognize this. Fluorine, you may often, I kind of talked about that before. Very, you know, we don't really come across fluorine because fluorine, the reactivity, the reaction is a little bit different than the rest of the halogen. The reason you don't have to know, but basically we don't often see fluorine as the reagent in organic chemistry. Okay, so bromine and chlorine. Now you may ask, hey sir, do we have to specify gaseous state or dissolve in organic solvent or dissolve in water? Now again, do you see it is necessary in these guidelines? You see no. So you don't have to. You don't have to show that it is chlorine gas, bromine liquid, something like that. You don't have to. Okay. Now, but this one, okay, bear in mind, guys. Okay, you don't have to show the physical state. Only in this kind of questions. Like here, it is perfectly fine to put down Br2. Okay. But if the question asks you, suggest a test, suggest the reagent, then I don't think you can put down Br2 because elemental Br2 is highly toxic and it is seldom used in a chemical synthesis in a laboratory scale. Okay, so very often the bromine will either dissolve in water or dissolve in organic solvent. Okay, so bear in mind, what I'm trying to show you here is only applicable when we are dealing with synthetic route synthesis reactions. If the question asks you another way round, it would be best if you specify as much as you can. Okay, so here, let's look at alkene. Alkene, we have addition reaction, right? So we can have alkene reacts with halogen. So the halogen could be chlorine, bromine, iodine. Okay. Now here, we specify that it is in organic solvent because if this is in water, then it will generate a halo alcohol, if you remember. So this one, you need to specify that it is in organic solvent. So it could be maybe hexane or ether, this kind of organic solvent, okay? Alkene can also react with hydrogen to form alkane. So remember, if you use platinum as a catalyst, you don't have to heat it. If you use nickel, you have to heat it, okay? So you see, we have a couple of different suitable catalysts, okay? But my advice is you use platinum because you don't have to heat it, okay? Alkene can also react with a hydrogen halide to form alkane. This one is often in gaseous state. So here you see HX, this time it includes HF, okay? And this one, you see, it also wants you to predict the major product using Markovnikov rules, okay? Remember, the hydrogen is added to the less substituted carbon, or you can think about the halogen is added to the more substituted carbon. Both way will do. So when you are doing synthesis, especially when you're writing the intermediate or the final product, make sure you pay attention to the Markovnikov rule, okay? Now, for haloalkane, there is only one reaction. It is to react with sodium hydroxide to form alcohol. Now you see, for sodium hydroxide, you need to specify the physical state because it does not react with solid sodium hydroxide. It only reacts with sodium hydroxide solution. So this is a substitution reaction forming alcohol, okay? Now you see, well, this one is for us teacher. For you, you don't have to know, okay? You don't have to know. Okay, next page. Here, alcohol can be converted into haloalkane. Again, it's a substitution reaction. And if you remember, for this one, I spent quite a lot of time talking about how this reaction actually takes place. Because with HCl, HBr, HI, they may require different conditions. If you remember, it is okay to use corn hydrochloric acid to accomplish the conversion. You don't even have to heat it. But in reality, if you want to prepare, let's say, alcohol reacts with HBr, actually it is not, this is not ideal because HBr, the Br minus, will be readily oxidized to form bromine. So we say that for that reaction, we want to prepare the HBr in situ. Okay, we want to prepare the HBr in situ. Okay, same as HI. Okay, so this is the difference between how we actually do it and how we will present it in synthetic route. For synthetic route, you only have to show the key reagent. Okay, you don't have to consider all the detailed conditions or all the procedures. Okay, so here, no matter which halogen are you trying to do the substitution, it doesn't matter. You can use HCl, HBr, HI, PCl3, PBr3, PI3. They are all perfectly fine. Some textbooks may use PX5, let's say PCl5, PBr5. Those are okay, but again, I will try to follow the guide, okay? Now, here, alcohol can also undergo dehydration. So there are two ways, whether you go for a dehydrating agent or you use a catalyst. No matter which one, you must heat it. Okay? Now, for alcohol, primary alcohol can undergo oxidation to form aldehyde or carboxylic acid. Depends on how you conduct the experiment, whether you do a heat under reflux or you do a distillation. But you see here, you don't have to specify whether you go for reflux or you go for distillation. All you have to show is it requires heating, and that's it. Okay? Now, also pay attention here. K2Cl2O7/H+. What do you mean by /H+? So here, doesn't mean or. The slash here doesn't mean or. This slash means together with. Together with. Okay? So this is like the notation we use when we talk about synthetic routes. So this one basically means the potassium dichromate is dissolved in an acid. So that means it is acidified. Okay? Now, the secondary alcohol, it can also undergo oxidation, but this time it forms ketone. It forms ketone, okay? Now, you may ask, hey, sir, can we do potassium permanganate? Yes, we do. But if you use potassium permanganate, you cannot get aldehyde. You can only get carboxylic acid. So that's why in this guide, we would suggest you to use potassium dichromate because you can produce aldehyde as well as carboxylic acid. So yeah, I would recommend you to use potassium dichromate as well. Now, aldehyde and aldehyde ketone, these can be reduced back to the alcohol, okay? So it could either be lithium aluminum hydride or sodium boron hydride. If you remember, for lithium aluminum hydride, it must be used together with dry ether. Kind of magnify a little bit. You must use a dry ether. And remember, it's 2 steps. One, reduction. Second one, you need to add acid to not only remove unreacted lithium aluminum hydride, but also to convert the alkoxide ion back to the alcohol. Okay? Now, if you forgot about that, you can go back to part 1. But at least you need to know, whenever we use lithium aluminum hydride, remember, 1, 2, 1, 2. Okay? Now, you can also use a milder version of reducing agent, sodium boron hydride, but bear in mind, this one is only capable of reducing aldehyde and ketone. It cannot be used to reduce carboxylic acid. Okay? Now, for sodium boron hydride, it's perfectly fine to be used in aqueous solution. Okay? So that's the idea. Now, here, aldehyde, basically the same as the primary alcohol, can be further oxidized into carboxylic acid, same reagent condition. Okay? Now, for carboxylic acid, so here, carboxylic acid reacts with alcohol to form ester and water. And the catalyst we use is concentrated sulfuric acid. The condition is heating. Okay, heating. Now, you see this reaction is reversible. Okay, it's reversible, bear in mind. But when you are describing the synthetic route, you don't have to specify the reversible arrow. You just use one-headed arrow, that would be fine. Again, it's not a reaction in synthetic route. It is basically a synthesis, okay? So you don't have to use a reversible sign for synthetic route, okay? Now, carboxylic acid can also be reduced back to alcohol using lithium aluminum hydride, okay? Same condition as the reduction of aldehyde and ketone. And then carboxylic acid can be converted into unsubstituted amide by 2 methods. The first one, we will treat it with PCl3, which actually changing the carboxylic acid into acyl chloride, if you remember. And then we will substitute the acyl chloride by the ammonia, forming unsubstituted amide. So 2 steps. Carboxylic acid can also convert it into unsubstituted amide using ammonia gas with heating or ammonia solution with heating. Okay, so both methods you need to know. One requires heating, one does not. Okay, but this one requires 2 steps, and PCl3 is considered more hazardous, more reactive, because it's so sensitive to water. Okay. Now, ester, you can have only one reaction, hydrolysis. But for hydrolysis, we have 2 types. We have acidic hydrolysis or acid catalyzed hydrolysis. We also have alkaline hydrolysis. So if you go for acidic hydrolysis, acid catalyzed hydrolysis, so again, it is a reversible reaction. You need to add a dilute acid and you need to heat it. Okay, the reaction itself is reversible. Basically, the opposite of esterification. So that's why it is also reversible. Okay, for alkaline hydrolysis, ester will first hydrolyze by a dilute strong base, such as sodium hydroxide, requires heating. And after that, you realize that in an alkaline medium, the carboxylic acid actually exists as carboxylic ions. So that's why we need to add excess dilute acid, not only to neutralize the unreacted base, but also to convert the carboxylic ion back to the carboxylic acid. Okay, so that's why we need to have 2 steps. Is that clear? Now, here, the last one may be the most complicated one because you see, wow, we have like 4 equations. But actually, all of them are hydrolysis. And this one, they take care of the acid alkaline property of carboxylic acid and the amine. Okay, so the first one here, we are trying to do alkaline hydrolysis. So our target is to form carboxylic acid. Okay, so that's why at the end we try to acidify it so that we get the carboxylic acid. So the unsubstituted amine, you can treat it with sodium hydroxide, heat it, so they will form carboxylate ion and ammonia. And then you will treat it with excess acid. So under an acidic medium, the carboxylate ion converted back to carboxylic acid, and the ammonia will accept the H+, become ammonium salt. Okay? So bear in mind the acid-alkaline behavior of the product when it comes to the hydrolysis of amine and hydrolysis of esters. Okay? If this is N-substituted amine, actually the reaction is the same, but just that the product is not ammonium, should be acal ammonium. Okay? Now, I understand some of you may not be that familiar with this. Let me help you. So ammonium salts, we are talking about this. Okay? NH4+. Now, it depends on the acid, because usually acid, it has a negative ion. Hydrochloric acid, you have chloride. Sulfuric acid, you have sulfate. So it depends. It will form different salts based on different acid that you use. But ammonium salts, you can think about it this way. For acal ammonium salt, basically it is having acal group substituted to the ammonium salt. Okay. So because this time we are trying to hydrolyze an N-substituted amine. An N-substituted amine basically means we have an amine, and the N here is not just NH2, but perhaps with other AQ groups. Okay. So that's why when you hydrolyze the amine bond, it will produce the amine. And amine in an acidic condition will give rise to acal ammonium salt. So that's the idea. Now, for the unsubstituted amine, you can also do an acid hydrolysis. When you use acid hydrolysis, it will give you carboxylic acid. So one step, okay? And the corresponding nitrogen-containing compound will be ammonium salt because it is acidic condition, okay? So that's the idea. So these are all the important reactions, and how do we describe them in synthetic route? Okay. Now, next page is very beautiful because you see this is the organic synthesis map. Okay, I try to design these 2 pages for you to use it as a summary. Okay. So you can always revisit this page to get all the reactions and how we can change different compound to another compound based on their functional group, based on their homologous series. Okay, so it's just like an MTL map. Okay, so that could be helpful. Actually, it could be helpful if you have this map in your mind, and when the question asks you, okay, how can you change alcohol to ester, then if you have this picture in your mind, you know that, oh, you can have alcohol first converted into carboxylic acid and then to ester. Okay, so this is how you can accomplish the organic synthesis question. Okay, but you realize that there are something missing. Okay, there are something missing. What it is? Of course, it's the reagent, condition, catalyst, blah blah blah. It's all missing, right? It's all missing. This is the reason why, is because I try to do it with you. I try to, again, treat it as a revision. We try to finish off the map together. So you get even better impression to the synthesis, to the reaction. So I will try to follow the color from here. So Red will be the compound, so I don't have to use red. Reagent, I will use blue. Catalyst, I will use green. Condition, I will use purple. Do I have a purple? I don't have a purple. So for condition, I will use red then. Okay? So I will use different colors. So let's start with alkene, shall we? Alkene. So alkene can be converted into alkane, right? So what reagent? Of course, hydrogen, H2. Okay? And what else do we need? Of course, a catalyst. Okay? And the catalyst, what color did I use? Oh, the green one. Okay? So PT, platinum. Okay? You don't have to heat it. You don't have to heat it. Okay? Right? And then we can also look at alkene here. If we have alkene converted into haloalkane, then we will add HXE, right? Hydrogen halide, HX. That's it. Now, of course, guys, if you are coming across with a real haloalkane that you know the halogen, for example, this is Cl, then you should put down HCl. Don't put down HX. Okay? You should put down HCl if it is actually Cl. Okay? Now, let's also do this one, right? Alkane to haloalkane. So this one is a free radical substitution reaction. So we will use the corresponding halogen. Okay? So Xe2. Okay? And we also need what? We also need a specific condition, which is UV light. UV light or heat. Okay? But I would like to have UV. Okay? Now, let's go to the top here. Alkene to dihaloalkane, what should we use? Of course, we will use the halogen, okay? So the halogen would be X2, okay? X2, all right? So it would be best if you say in organic solvent, okay? Okay, and then this one, alkene to diol. This one, if you remember, this is potassium permanganate. Okay, so it's potassium permanganate in alkaline medium. Okay, in alkaline medium. Okay, do you have to heat it? No, you don't heat it. Okay. Because if you heat it, it will undergo further oxidation. Okay? Alright, so let's go to here. Now you see, alkene cannot be converted into primary alcohol. Actually, it can. We will do a hydration. So first with corn sulfuric acid and then heat it with water. But that one is out of syllabus. So that's why I didn't show you the reaction from here to here. So you realize that if you want to change alkene into alcohol, you need to go this way. First convert it into haloalkane and then perform a substitution reaction. Okay? Maybe we start from here. Okay, shall we? So alkene becomes haloalkane. How haloalkane can be converted to alcohol? So of course, this one is a substitution reaction with sodium hydroxide, AQ. Right? Sodium hydroxide, AQ. Okay? You don't have to heat it. Okay? Now, let's look at alcohol. You see, alcohol has so many reactions. Right? You can have this one, okay? There are many reactions, right, for alcohol. So first of all, alcohol, it can actually go back to the haloalkane by performing substitution reaction. This time, you can have the hydrogen halide or the phosphorus trihalide. For me, I like phosphorus trihalide, so I do PX3. PX3, okay? Just like that. No need to heat, okay? Now, primary alcohol can be converted back to alkene. So this reaction is obviously dehydration. So again, it depends on which type you want to use. For me, I would like concentrated sulfuric acid, like concentrated sulfuric acid. And then for this one, you must heat it. Okay, concentrated sulfuric acid. Of course, you can also use Al2. You can also choose to use Al2O3. Okay, there are two types. For Al2O3, it is a catalyst. For concentrated sulfuric acid, now strictly speaking, it is not a reagent. It's a dehydrating agent. I think it is a I think it is a reagent. Okay, con sulfuric acid. Yeah, it did participate in the reaction, but does it generate at the end? So if you check the reaction, if you simply write down the reaction, it is the alcohol become alkene plus a mole of water. So it does not include the con sulfuric acid as the reagent. So con sulfuric acid is not really the reagent, but it does participate in the reaction. It's more like a catalyst, I think. But anyway, we don't often say it as a catalyst in this reaction. We usually say it is a dehydrating agent. So probably con sulfuric acid does not fall into any one of those reagent, condition, catalyst. Maybe something else. Maybe what we call auxiliary agent. Okay, chemical auxiliary. But this is something else. Anyway, here you see haloalkane can undergo substitution not only to primary alcohol but also to secondary or even tertiary alcohol. So the reaction actually is the same. No matter it is which primary, secondary, tertiary. If you want to change the haloalkane into alcohol, you do a substitution reaction. So all of these, sodium hydroxide AQ, that's it. Okay? Sodium hydroxide AQ. Okay? Now, so for all these primary alcohol, secondary alcohol, tertiary alcohol, if they want to go back to the alkene, they undergo dehydration. So I don't repeat myself too much. Okay? So now, let's also look at alcohol. The other reaction is the oxidation reaction. So for oxidation reaction, primary alcohol becomes aldehyde, becomes carboxylic acid. They all require an oxidizing agent such as dichromate. Remember, in acidic conditions, and also remember, heating is necessary. Heating. Okay? Heating. Okay? So it would be the same for secondary alcohol. Okay? K2Cl2O7, H+, and then heat. Okay? Actually, this one, aldehyde to carboxylic acid, same. K2Cl2O7, heat. Okay? Actually, we better put this one at the bottom here. Sorry. Better put this one here. Okay? Alright? And then, aldehyde, ketone, carboxylic acid, they can all be converted back to alcohol. So that one will be a reduction. So reduction, you will do LiAlH4. Okay, let me make it a little bit bigger. LiAlH4, okay, in dry ether. And then we add acid. Now acid, you see in the chemistry guide, they simply use H+, but for me, I would like to use an actual acid, so probably I will do H2SO4, okay? Dilute H2SO4, okay? So similarly, for all this reduction, okay, just like that. So lithium aluminium hydride. better to memorize this because this one is the powerful reducing agent that can reduce basically all the organic compounds, the aldehyde, ketone, carboxylic acid. If you use sodium boron hydride, it doesn't work for carboxylic acid, so that's why. Okay, bear in mind carboxylic acid cannot be reduced to aldehyde directly. You need to first reduce back to the alcohol and then perform a mild oxidation with acidified potassium dichromic solution. Okay? Okay, and then to carboxylic acid. Carboxylic acid, it can be converted into esters. Okay, it can be converted into esters, and this conversion is reversible. Okay, so this one, you need to first of all use an alcohol. So an alcohol is the reagent. So I would say it's alcohol. Okay. Or simply ROH, it doesn't matter. I think ROH is better because ROH, you need an alcohol and then you need a catalyst, which is corn sulfuric acid, and you must heat it. Okay? So all three items are necessary. Okay? So this is how carboxylic acid becomes esters. Now, carboxylic acid can also become unsubstituted amide. This one, you can use ammonia, and then you heat it. Or you can do what? You can have two steps. First, PCl3, second, ammonia. So two steps, both are acceptable. Okay? Now, ester has only one reaction, hydrolysis. No matter it is acid hydrolysis or alkaline hydrolysis, both works. Okay? So here I use a reversible sign, so I'll try to do an acid hydrolysis. So I will have H2SO4, and then I should use this one. Actually, this is not the reagent, but anyway, heat. It's more like a catalyst, but I don't want to get too detailed on that. Okay. So amide becoming carboxylic acid. Again, you can do acid hydrolysis. You can do alkaline hydrolysis. But since we try to form carboxylic acid instead of carboxylic ion, so that's why you do acid hydrolysis. Actually, both will do. So again, you can use an acid of your choice, and then you will heat it. Okay? So that's the idea. So you see, this is the whole picture. Okay? So this one could be a good revision. Quick look at all the reactions. Now, you see, there are some reactions requires heating, right? Heating, right? Heating, right? So actually, which type of reaction requires heating? So you may put it, maybe I use the space here. So I try to summarize all the reaction requires heating. Okay? Reactions requiring heating. So what are the reactions that requires heating? First of all, dehydration. No matter which type of dehydration, you must require heating. So dehydration is like ROH becomes alkene. Okay? Alcohol becomes alkene. You must heat it. Okay, the second one is oxidation. Oxidation, you must require heating. For example, like ROH to RCHO to RCOH, this kind of thing, you must require heating. Okay? The third one that you must require heating is esterification. Okay? Or we say condensation. Okay? So of course it will be carboxylic acid becoming an ester. Okay? It also applicable because condensation. It also applicable to the formation of amide. But the formation of amide, you can use PCl3 followed by NH3. In that case, you don't have to heat it. So that's why I try to focus on the esterification. Okay. The fourth type is hydrolysis. Hydrolysis, no matter it is acid hydrolysis, alkaline hydrolysis, okay, it must require heating. Also, no matter it's ester or amide, you must heat it. Okay. So here, basically, we're trying to say ester becoming acid. Okay. So these reactions require heating. And there's actually one more, which is polymerization. Even though it is not specifically concerned in the organic synthesis map, but polymerization requires heating. This is quite obvious. Okay? So those are the reactions that requires heating that may solve your problem of whether you should heat it or not. Now you may ask, what if I put down heating in some reaction that does not require heating? Is it considered right or wrong? It depends. It depends whether the heating will affect that particular compound and whether that heating will lead to a side reaction. So, for example, if you try to do, for example, a substitution reaction, okay, for alcohol to haloalkane. You see, you don't have to specify heating, right? Okay, alcohol and haloalkane. You don't have to heat it, right? So, what if you put down heat? Now, chances are, if you heat it, then it may undergo dehydration. Okay? Or in some situation, okay, but some situation, if you heat it, it doesn't matter. Like for example here, alkene to alkane. With hydrogen platinum, if you heat it, it's fine. There should not be any problem if you heat it. So this is the reason why I need to specify which reaction requires heating. If they do not require heating, you don't have to include the heating there. Okay? This is to avoid any possible side reaction that you don't know. Okay? So right now, page 74, 75, these are some practice questions regarding the synthesis. Now I will show you the first one and then your turn. So here, this is exactly the question wording I copied from DSC. This is exactly what they need you to do. Outline a synthetic route, no more than 3 steps, to accomplish the following conversion. For each step, reagent, condition, structure of organic products. Okay? Now it says no more than 3 steps, but most of the time 2 steps. Because if there are 3 steps, okay, then there will be 2 intermediates and 3 sets of reaction condition. And that will altogether be 5 marks, which is too much, right? So that's why most of the time it is 2 steps, okay? But you may also come across with some of these questions requiring 3 steps. So let me show you the first one. So the first one here, alkene to alcohol. If you got the map in your mind, alkene to alcohol, you need to first change it to haloalkane, and then you do a substitution to form the alcohol. Okay, so I will first react with HBrO. Okay, for example, now use the actual reagent. You don't use HX, right? Use the actual reagent. So I will form a haloalkane. All right, and then I will undergo a substitution reaction with sodium hydroxide, and boom, that would be the answer. Okay, so you see here, I took like 10 seconds and I got 3 marks already. 3 marks. So it's very important for you to be familiar with these type of questions, because you can get like a lot of marks in less than a minute. Okay, so now pause the video, spend some time to do B, C, D, E, F. Okay? So let's do it. Now, I assume you have done it, so let's check the answers. So here, chloro, alkane to ketone. So first, you need to change it into an alcohol, a secondary alcohol. Okay, this one is by a substitution reaction with sodium hydroxide, and then you follow by oxidation. So it is K2Cl2O7H plus heat. Okay, so that should do it. Next one, haloalkane to esters. Haloalkane to esters. So now you realize that here the two carbons. This is the starting reactant, the two carbons. And here, this is an ester with 3 carbons. So you see the 2 carbon is from a carboxylic acid. This one must come from the haloalkane here. So first of all, you need to change the haloalkane into an alcohol. As a matter of fact, this is the only reaction for haloalkane, right? So when you come across with haloalkane, you don't have to think. You need to change it into an alcohol, right? Because there are only one reaction, okay? Into alcohol, this one you use sodium hydroxide. And then perhaps you need to oxidize it all the way to carboxylic acid. Okay, so you use K2Cl2O7H plus heat. Okay, and then from here you hear it is an esterification. So esterification, you need the alcohol. So in this case, you need methanol. Okay, because this methanol will be here, right? Okay. So and then you need corn sulfuric acid, and you also need to heat it. Okay. So that's the idea. Okay, D. Part D. So we have an ester changing into alcohol. Ester into alcohol. So ester, the only reaction is to hydrolyze it. So you can hydrolyze it using acid hydrolysis, right? So it will form this one. Okay, so acid hydrolysis, you can use H2SO4, and remember, whenever it is hydrolysis, you need to heat it. Okay, and then for carboxylic acid to alcohol, you need to do 1 lithium aluminum hydride in dry ether, followed by H2SO4 or H+. Okay, so that should do it. Now here, what we are doing here is to change the halogen. Okay. Now you see, it is from the 3rd position to the 2nd position. Oh, do we have to change the position? Actually, if you are smart, you realize that no matter you put it this way or this way, both halogens are located on the 2nd position. So you don't have to change the location actually. So to do this, we need to change the halogen into alcohol and then change it back to halogen. Okay? So you can change it into alcohol by doing a substitution reaction. Then you can substitute the alcohol by PBr3. Done. Okay? That should do it. Okay? And lastly, looks complicated. So this time the compound has 2 functional groups. We have the CC double bond and this one. Now you may think, oh, is it an ester? No, it is not. This is actually, so there should be three functional group. We have CC double bond, hydroxyl group, and also an ether. But you know, ether, we don't have any chemical reaction for ether, so you can sort of ignore the ether. Okay. Now at the end, we should have only the ether is left. So the hydroxyl is gone, the CC double bond is gone. Okay. So this one could be quite tricky. The way of doing this is, first, you do dehydration. you do a dehydration. So when you do dehydration, you should form another double bond, another CC double bond. So basically, think about here we have an H, and then you take away this one, you take away this one, okay? Forming the water, and then this one becomes a CC double bond. So this is a dehydration. So for dehydration, we can use corn sulfuric acid, and then we heat it. Okay, dehydration must require heating. And then you do a hydrogenation, right? You do a addition reaction with hydrogen. So H2, PT, platinum as the catalyst. So you will form this one. Okay? So that's the idea about organic synthesis. And there should be more questions at the back here, page 82. So if you're interested, you can try to do these questions. These are more complicated. There are 12 of them, okay? So that's it for today. See you guys later in the next video. Bye-bye.